Hello friends, welcome to another episode of Learn with Projects. Today we will be covering machine learning part 1. First question is root mean square error. Root mean square error is the measure of how well a regression line fits the data points. RMSE is often preferred over MSC or mean squared error for several reasons, primarily due to its interpretability. It is directly related to the model fit, easy to compute, differentiable, useful for optimization in the same unit as the response variable, making it easier to interpret and relate to the problem. Key reasons for preferring RMSC is its interpretability and second, it is sensitive to large errors. RMSC increases more with large errors due to the squaring before the root, emphasizing significant dispenses between the predicted and actual values. The characteristics makes it easier for stakeholders to understand the magnitude and prediction errors, facilitating more information, more informed decisions based on the model's output. Second is mean absolute error or MAE. Mean absolute error calculates the average difference between calculated values and actual values. It is also known as scale dependent accuracy as it calculates error in observations taken on the same scale used to predict the accuracy of the machine learning model. Mean absolute error is calculated by taking the summation of absolute difference between the actual and calculated values of each observation over the entire array and then dividing the sum obtained by the number of observations in the array. Why to choose mean absolute error? Mean absolute error is important metric to assess the performance of regression models. Several key reasons why MAE is significant and widely adopted are: first is interpretability. It provides a straightforward measure of an average error, calculating the average absolute difference between predicted and actual values. Second is robustness to outliers. MAE is resilient to outliers, treating all errors equally, unlike mean squared error, which penalizes large discrepancies more heavily, and MAE maintains stability and reliability when the dataset includes outliers. Third, practical application. MAE is useful in real-world scenarios where the error costs are linear, such as demand forecasting or house price estimation. It offers insights into average error sizes, making it preferred metric for evaluation, prediction, equality based on absolute rather than relative error. For this linear penalty, the linear nature of MAE means that each error's impact on model learning is directly proportional to its magnitude. This allows the model to minimize average errors without disproportionately focusing on larger discrepancies, ensuring balanced performance across all data points. Mean absolute error or MAE is a vital metric for evaluating regression models in machine learning. Its clear interpretation of average prediction errors, robustness to outliers, practicality in the real-world application, making it essential tool for assessing model performance. By focusing on minimizing overall errors without disproportionately penalizing large discrepancies, MAE promotes balanced learning. R squared or coefficient of determination. R squared, also known as coefficient of determination, is a statistical measure that represents the proportion of the variance for dependent variable that's explained by one or more independent variables in the regression model. In simple terms, it shows that how well the data fit a regression line or a curve. The coefficient of determination, which is represented by R2, is determined using the following formula. R2 is equals to 1 minus into the bracket residual sum of squares divided by total sum of squares. The coefficient of determination or R square has following advantages. It helps to predict the value of one variable according to other. Second, it helps to check accuracy of making predictions from given data model. It helps to predict the degree of association among various variables. The coefficient of determination lies in the range of 0 to 1. If the coefficient of determination is 0, then the variables are independent and the value of variable cannot be predicted at all from the value of the second variable. If the coefficient of determination is 1, then the variables are completely dependent and the value of variable can be accurately predicted from the value of second variable. Any other value tells the extent of determination of the value of variable. The higher the value, higher is the accuracy of the determination. Disadvantages of R squared value. The coefficient of determination has following disadvantages. It does not tell the fitness of the model and does not consider the bias that the model may exhibit. It is not useful to explain reliability of the model. The value of R squared can be low even for very good model. Absolute percentage error or simply MAPE. It also known as mean absolute percentage deviation MAPD in Python. The MAPE term determines how better accuracy does our forecast gives. The M in MAPE shows for mean which takes the average value over series. A stands for absolute that uses absolute values to keep positive and negative errors from cancelling one another. P is a percentage that makes this accuracy metric relative metric, and E stands for error since the metric helps determine the amount of error our forecast has. MAP output is non-negative floating point. The best value for MAP is 0, whereas the higher value for determines the predictions are not accurate enough. What is confusion matrix? A confusion matrix that summarizes the performance of machine learning model on a set of test data. It means displaying the number of accurate and inaccurate instances based on the model's predictions. It is often used to measure performance of classification models which aims to predict categorical label for each input instance. The matrix displays the number of instances produced by the model on the test data. True positive. The model correctly predicted positive outcomes. The actual outcome was positive. True negative. TN. The model correctly predicted the negative outcome. The actual outcome was negative. False positive. The model incorrectly predicted a positive outcome. The actual outcome was negative, also known as type 1 error. False negative. The model incorrectly predicted a negative outcome. The actual outcome was positive, also known as type 2 error. When assessing classification models' performance, a confusion matrix is essential. It offers a thorough analysis of true positive, true negative, false positive, false negative prediction, facilitating a more profound comprehension of a model's recall, accuracy, precision, and overall effectiveness in class distinction. When there is an uneven class distribution in a dataset, this matrix is especially helpful in evaluating a model's performance beyond basic accuracy metrics. Metrics based on confusion matrix data. First is accuracy. Accuracy is used to measure the performance of the model. It is the ratio of total correct instances to total instances. Second is precision. Precision is a measure of how accurate a model's positive predictions are. It is defined as the ratio of true positive predictions to the number of positive predictions made by the model. Third is recall. Recall measures the effectiveness of classification model in identifying all relevant instances from dataset. It is the ratio of number of true positive instances to the sum of true positive and false positive instances. We use precision when we want to minimize false positive. Crucial in scenarios like spam email detection where misclassifying a non-spam message as a spam is costly. And when we use recall, when minimizing false negativeness is essential, as in medical diagnosis where identifying all actual positive cases is critical. Even fourth is F1 score. F1 score is used to evaluate the overall performance of a classification model. It is harmonic mean of precision and recall. We balance precision and recall with the F1 score when trade-off between minimizing false positive and false negative is necessary. Such an information retrieval system. Specificity. The specificity is another important metric in evaluation of classification models, particularly in binary classification. It measures the ability of models to correctly identify negative instances. Specificity is also known as true negative rate. Sixth is type 1 and type 2 error. Type 1 error occurs when the model predicts the positive instances but it is actually negative. Precision is affected by false positive as it is the ratio of true positives to the sum of true positive and false positive. Type 2 error. Type 2 error occurs when the model fails to predict the positive instances. Recall is directly affected by false negative as it is the ratio of true positive to the sum of true positives and false positives. In the context of medical testing, type 2 error, often known as false negative, occurs when the diagnostic test fails to detect the presence of disease in the patient who genuinely has it. The consequences of such error are significant as it may result in delayed diagnosis and subsequent treatments. Next is ROC AOC curve. The ROC and AOC curve or area under the AOC and ROC curve or area under the receiver operating characteristics curve is graphical representation of performance of a binary classification model at various classification thresholds. It is commonly used in machine learning to assess the ability of model to distinguish between two classes. Typically the positive class, for example presence of a disease, and the negative class, that is absence of a disease. Receiver operating characteristics ROC curve stands for receiver operating characteristics, and ROC curve is general graphical representation of effectiveness of the binary classification model. It plots the true positive rate TPR versus false positive rate FPR at different classification thresholds. Area under curve AOC curve. AOC stands for area under the curve and AOC curve represents the area under ROC curve. It measures overall performance of binary classification model as both TPR and FPR range between 0 to 1. So the area will always lie between 0 to 1 and a greater value of AOC denotes better model performance. Our main goal is to maximize this area in order to have highest TPR and lowest FPR at the given threshold. The AOC measures the probability that model will assign a randomly chosen positive instance a higher predicted probability compared to the random chosen negative instances. Key terms used in AOC and ROC curve are TPR and FPR. This is the most common definition. Basically, ROC curve under ROC curve that plotted between two parameters TPR and FPR. TPR is true positive rate and FPR is false positive rate. Second is sensitivity or true positive rate or recall. Basically, TPR or recall or sensitivity is the ratio of positive examples that are correctly identified. It represents the ability of the model to correctly identify positive instances and is calculated as TPR is equals to TP, that is true positive, upon into the bracket true positive plus false negative. Sensitivity measures the proportion of actual positive instances that are correctly identified by the positive model as positive. Third is false positive rate. False positive rate is the ratio of negative examples that are incorrectly classified. And specificity is the measure of proportion of actual negative instances that are correctly identified by the model as negative. It represents the ability of the model to correctly identify negative instances. Relationship between sensitivity, specificity, FPR and threshold. Sensitivity and specificity. There is inverse relationship. When one increases, the other tends to decrease. This reflects the inherent trade-off between true positive and true negative rates. Turning via threshold. By adjusting the threshold value, we can control the balance between sensitivity and specificity. Lower threshold leads to higher sensitivity, more true positives at the expense of specificity, more false positive. Conversely, raising the threshold boosts specificity, fewer false positives, but sacrifices sensitivity, more false negatives. Relationship between threshold and false positive rate. False positive rate is simply the complement of specificity, that is FVR is equals to 1 minus specificity. This signifies the direct relationship between them. Higher specificity translates to lower FPR and vice versa. FPR changes with TPR. Similarly, as the true positive rate and false positive rate are linked, the increase in TPR, more true positives, generally leads to a rise in a false positive rates. Conversely, a drop in true positive rate, fewer true positives results in a decline in false positive rates. When should we use the AOC ROC evaluation metric? There are some areas where using AOC and ROC might not be ideal. In cases where dataset is highly imbalanced, the ROC curve can give an overly optimistic assessment of the model's performance. This optimism bias arises because ROC curve's small positive rate can become very small when the number of actual negatives is large. Speculating performance of the model. A high AOC that is close to 1 indicates excellent discriminating power. This means that the model is effective in distinguishing between two classes. Its predictions are reliable. A low AOC close to 0 suggests a poor performance in case the model suggests to differentiate between positive and negative classes, and its prediction may not be trustworthy. AOC around zero point 0.5 implies that the model is essentially making random guesses and it shows no ability to separate the classes, indicating that the model is not learning any meaningful patterns from the data. Second questions. Assumptions of linear regression. Key assumptions of linear regression are: first, linearity. The assumption is the relationship between independent and dependent variable is linear. The first and foremost assumption of linear regression is that relationship between the predictors and the response variable is linear. This means that a change in independent variable results in proportional change in dependent variable. This can be visually addressed using scatter plots or residual plots. If the relationship is not linear, the model may underfit the data, leading to inaccurate predictions. In such cases, transformations of the data or use of the nonlinear regression model may be more appropriate. Second assumption is homoscedasticity of residual in linear regression, which asserts that the residuals or the difference between observed and predicted values should have constant variance across all levels of the independent variable. In similar terms, it means that spread of the error should be relatively uniform regardless of the value of the predictor. When the residual maintain constant variance, the model is said to be homoscedastic. Conversely, when the variance of the residual changes with the level of independent variable, we refer to this phenomenon as heteroscedasticity. Heteroscedasticity can lead to several issues. Inefficient estimates. The estimates of the coefficient may not be the best linear unbiased estimators, meaning that they could be less accurate than they should be. Impact on hypothesis testing. Standard errors can become biased, leading to unreliable significance tests and confidence intervals. Third is left plot. Homoscedasticity. The residuals are scattered evenly around the horizontal line at 0, indicating constant variance. Right plot. Heteroscedasticity. The residuals are not evenly scattered. There is a clear pattern in increasing variance as the predicted values increase, indicating heteroscedasticity. Third assumption is multivariate normality or normal distribution. It is a key assumption for linear regression models when making statistical inferences. It means that residuals, the difference between the observed and predicted values, should follow a normal distribution when considering the multiple predictors together. This assumption is crucial because it allows us to make valid inferences about models' parameters and the relationship between dependent and independent variables. Fourth assumption is independence of errors. Independence of errors is another crucial assumption for linear regression model. It ensures that the residuals or the difference between observed and predicted value are not correlated with one another. This means that error associated with the observation should not influence the error of any other observation. When errors are correlated, it can indicate that some underlying pattern or trend in the data has been overlooked by the model. If the errors are correlated, it can lead underestimated standard errors, resulting in overconfident predictions and misleading significant tests. Violation of this assumption is most common in the time series data, where the error at one point in time may influence error at subsequent time points. Such patterns suggest that the presence of autocorrelation. Fifth assumption is lack of multicollinearity. The independent variables are not highly correlated with each other. Multicollinearity occurs when two or more independent variables in the model are highly correlated, leading to redundancy in the information they provide. This can inflate the standard errors of the coefficients, making it difficult to determine the effect of each independent variable. When multicollinearity is present, it becomes challenging to interpret the coefficients of the regression model accurately. It can also lead to overfitting, where the model performs well on the training data but poorly on unseen data. We can identify highly correlated features using scatter plots or heat map. Sixth assumption is absence of endogeneity. No endogeneity is an important assumption in the context of multiple linear regression. The assumption of endogeneity states that the independent variables in the regression model should not be correlated with error term. If this assumption is violated, it leads to biased and inconsistent estimates of the regression coefficients. Bias and consistency: when endogeneity is present, estimates of the regression coefficients are biased, meaning they do not accurately reflect the true relationship between the variables. Additionally, the estimates become inconsistent, which means they do not converge to the true parameters values as the sample size increases. The valid inference: the assumption of no endogeneity is crucial for conducting valid hypothesis tests and creating reliable confidence intervals. If endogeneity exists, the statistical test based on these estimates may lead to incorrect conclusions. How to address violations of assumptions? If any assumptions are violated, there are various strategies to mitigate the issue. Transformation: apply the transformation, that is logarithmic square root to the dependent variable to address non-linearity and heteroscedasticity. Adding variables: if autocorrelation or omitted variables bias is suspected, consider adding the relevant predictors to the model. Regularization technique: the technique like ridge or lasso regression can handle multicollinearity and improve model's performance. Robust regression: consider using robust regression methods such as quantile regression or Huber regression that are less sensitive to violation of assumptions. Generalized least squares: this approach can be used when the residuals are heteroscedastic or correlated. Next question is R squared versus adjusted R square. The prime difference between R square and adjusted R square lies in how they account for the number of predictors in the regression model. R squared measures the proportion of variance in the dependent variable explained by the independent variable. It always increases when more predictors are added, regardless of their relevance to the model. In generalized linear regression model, the model accuracy ranging from 75 to 95% considered as good prediction model, whereas 100% accuracy means overfitting. R squared values ranges from 0 to 1. Value closer to 0 explains none of the variability in the dependent variable, and the closer to 1 explains all the variability of the dependent variable. Adjusted R square, on the other hand, adjusts the R squared value based on the number of predictors of the model. It accounts for degree of freedom, penalizing the addition of irrelevant predictors. As a result, adjusted R squared can decrease if a new predictor does not improve the model sufficiently. A higher adjusted R square indicates that the model fits the data well without including unnecessary predictors, suggesting that the chosen features are meaningful and contribute to the explaining the variability in the dependent variable. On the other hand, a lower or negative adjusted R square suggests that adding more predictors does not improve the model's performance and may even harm it. They occur when the extra predictors add noise rather than value. Adjusted R square can be negative if the R square is close to 0, indicating that adding predictors does not improve the model. Next question is, can you explain what is overfitting and how adjusted R square helps to prevent it? Overfitting happens when the model is too complex, having too many parameters relative to the number of observations. Adjusted R square helps to prevent overfitting by including penalty for number of predictors in the model. Unlike R squared, which always increases with the additional predictors, adjusted R square can decrease if the new predictors do not improve the model significantly. This discourages adding irrelevant variables and helps in selecting a more permissionless model. What is the situation where R square might be misleading? R square can be misleading in several situations. First is overfitting, second is non-linear relationship, third is comparison between different models. Comparing R square value between models when different numbers of predictors or different types of models, linear versus polynomial can be misleading as it does not account for model complexity. Next, what is the role of regularization? In Python, regularization is a technique used to prevent overfitting by adding a penalty term to loss function, discouraging the model from assigning too much importance to individual features or coefficients. First is complexity control. Regularization helps control model complexity by preventing overfitting to training data, resulting in better generalization to new data. Second is preventing overfitting. One way to prevent overfitting is to regularization, which penalizes large coefficients and constrains their magnitudes, thereby preventing a model from becoming overly complex, memorizing the training data instead of learning its underlying patterns. Third is balancing bias and variance. Regularization can help balance trade-off between model bias underfitting and model variance overfitting in the machine learning, which leads to improved performance. Feature selection. Some regularization methods, such as L1 regularization, that is lasso, promote sparse solutions that drive some features coefficient to 0. This automatically select the important features while excluding less important ones. Handling multicollinearity. When the features are highly correlated, regularization can stabilize the model by reducing coefficients sensitive to small data changes. Generalization. Regularized model learn underlying pattern of the data better generalization to new data instead of memorizing specific examples. In these, what are overfitting and underfitting? Overfitting is phenomenon that occurs when machine learning model is constrained to training set and not able to perform well on unseen data. That is when model learns the noise in the training data as well. This is the case where our model memorizes the training data instead of learning the patterns in it. Underfitting, on the other hand, is the case when the model is not able to learn even the basic patterns available in the dataset. In case the underfitting model is unable to perform well even on the training data. Hence, we cannot expect it to perform well on the validation data. This is the case when we are supposed to increase the complexity of the model or add more features to the feature set. What are bias and variance? Bias refers to the error which occurs when we try to fit statistical model on real world data which does not fit perfectly well on mathematical model. If we use way too simplistic model to fit the data, then we are more probably to face the situation of high bias, which refers to the case when the model unable to learn the patterns in the data at the hand and hence performs poorly. Variance implies the error value that occurs when we try to make predictions by using the data that is not previously seen by the model. There is a situation known as high variance that occurs when the model learns noise that is present in the data. Finding proper balance between the two, that is also known as bias variance trade-off, can help us prune the model from getting overfitted to the training data. Combinations of bias variance. First is high bias and low variance. A model that has high bias and a low variance is considered to be underfitting. High variance or low bias. A model that has high variance and low bias is considered to be overfitting. Third is high bias and high variance. A model with high bias and high variance cannot capture underlying patterns. It is too sensitive to training changes. On the average, the model will generate reliable and inconsistent predictions. Low bias and low variance. A model with low bias and low variance can capture data patterns and handle variations in training data. This is the perfect scenario for machine learning model where it can generalize well to unseen data, can make consistent accurate predictions. However, in reality this is not feasible. Bias variance trade-off. Bias variance trade-off is a fundamental concept in machine learning. It refers to the balance between bias and variance, which affect predictive model performance. Finding the right trade-off is crucial for creating models that generalize well to new data. The bias variance trade-off demonstrates the inverse relationship between bias and variance. When one decreases, the other tends to increase, and vice versa. Finding the right balance is crucial An overly simple model with high bias won't capture the underlying patterns, while an overly complex with high variance will fit the noise in the data. Regularization in machine learning. Regularization is a technique used to reduce errors by fitting the functions properly, appropriately on the given training set and avoiding the overfitting. The commonly used regularization techniques are lasso regularization, that is L1. Regularization is a regression model uses L1 regularization technique called lasso, that is least absolute shrinkage and selection operator regression. Lasso regression adds the absolute value of magnitude of the coefficient as a penalty term to loss function. Lasso regression also helps us achieve feature selection by penalizing the weights to approximately equal to 0 if that feature does not serve any purpose in the model. Second is ridge regularization, that is L2 regularization. A regression model that uses L2 regularization technique is called ridge regression. Ridge regression adds the squared magnitude of the coefficient as a penalty term to the loss function. Elastic neck regularization, that is L1 and L2 regularization. This model combination of L1 as well as L2 that implies that we add absolute norm of the weights as well as squared measure of the weights with the help of extra hyperparameters that controls the ratio of L1 and L2 regularization. What are the benefits of regularization? Regularization improves the model generalization by reducing overfitting. Regularized models learn underlying patterns while overfit model memorizes noise in the training data. Regularization techniques such as L1, L2 regularization, L1 that is lasso regularization simplifies model and improves the interpretability by reducing coefficient of less important features to 0. Regularization improves model performance by preventing excessive weighting or outliers or irrelevant features. Regularization masks the model stable across the different subset of the data. It reduces the sensitivity of the model output to minor changes in the training set. Regularization prevents model from becoming overly complex, which is especially important when dealing with the limited data in noisy environments. Regularization can help handle multicollinearity, that is high correlation between features, by reducing the magnitudes of correlated coefficients. Regularization introduces hyperparameters, that is alpha or lambda, that controls the strength of regularization. This allows fine-tuning models to achieve the right balance between bias and variance. Regularization promotes consistent model performance across different datasets. It reduces risk of dramatic performances changes when encountering the new data. Next question. Logistic regression in machine learning. Logistic regression is used for binary classification where we use sigmoid function that takes input as independent variable and produces probability value between 0 and 1. Logistic regression predicts the output of categorical independent variable. Therefore, the outcome must be categorical or discrete value. It can be either yes or no, 0 or 1, false or true, etc. But instead of giving the exact value as 0 and 1, it gives a probabilistic values which lie between 0 and 1. Logistic regression, instead of fitting a regression line, we fit an S-shaped logistic function which predicts two maximum values. Logistic function, a sigmoid function. A sigmoid function is a mathematical function used to map predicted values to probabilities. It may help real values into another value within the range of 0 to 1. The value of logistic regression must be between 0 and 1, which cannot go beyond this limit, so it forms a curve like S form. S-form curve is called sigmoid function or logistic function. A logistic regression, we use concept of threshold value, which defines the probability of either 0 or 1, such as values above the threshold value tends to 1 and a value below threshold value tends to 0. Types of logistic regression. On the basis of the categories, logistic regression can be classified into three types: binomial, multinomial, ordinal. Assumptions of logistic regression. First, independent observations. Each observation is independent of the other, meaning there is no correlation between the input variables. Binary dependent variables. It takes assumptions that dependent variable must be binary, meaning it can take only two values. Linearity relationship between independent variables and log odds. The relationship between independent variables and the log odds of the dependent variable should be linear. Fourth is no outliers. There should be no outliers in the dataset. Large sample size. Sample size should be sufficiently large. How does logistic regression work? Logistic regression transforms the linear regression function continuous value output into categorical value output using sigmoid function, which maps real valued set of independent variables input into a value between 0 and 1. This function is known as logistic function. We use the sigmoid function where the input will be z and v will be the probability between 0 and 1 that is predicted y. The odd is of the ratio something occurring to something not occurring. It is different from probability as the probability is the ratio of something occurring to everything that could possibly occur. Next question. Precision recall trade-off in logistic regression threshold setting. Logistic regression becomes a classification technique only when a decision threshold is brought into picture. The setting of threshold value is very important aspect of logistic regression and is independent of classification problem itself. The decision for the value of threshold value is majorly affected by the value of precision and recall. Ideally, we want both precision and recall being 1, but this seldom is the case. In case of precision recall trade-off, we use following arguments. First, low precision, high recall. In the application where we want to reduce the number of false positive without necessarily reducing the number of false positive, we choose a decision value that has a low value of precision or a value of recall. For example, a cancer diagnostic application, we do not want any affected patient to be classified as not affected without giving much need if the patient is being wrongfully diagnosed with cancer. This is because the absence of cancer can be detected by further medical diseases, but the presence of disease cannot be detected as an already rejected candidate. Second is high precision and low recall. In applications where we want to reduce the number of false positives without necessarily reducing the number of false negatives, we choose decision value that has high value of precision or low value of recall. For example, if we are classifying customers whether they will positively react or negatively to a personalized advertisement, we want to be absolutely sure that customer will react positively to the advertisement because otherwise a negative reaction can cause loss of potential sales from the customer. Difference between logistic and linear regression. Linear regression is used to predict the continuous dependent variable using a given set of independent variables. Logistic regression is used to predict the categorical dependent variable using a given set of independent variables. Linear regression is used for solving regression problems and logistic regression is used for solving classification problems. Linear regression predicts the continuous variable and logistic regression predicts the categorical variable. So we find best fit line in the linear regression and we find S curve in the logistic regression. The output must be continuous values such as price, age, etc. in the linear regression, but in the in logistic regression, it must be categorical such as 0 or 1, yes or no, true or false, etc. In linear regression, there may be collinearity between independent variables, but in logistic regression, there should be little to no collinearity between independent variables. How to handle imbalanced classes in machine learning. Using random undersampling, when observations from the majority class are eliminated until the majority and minority class are balanced, this is known as undersampling. Undersampling has advantages when worked with large dataset, especially ones with millions of rows, but there is a risk that important information will be lost during the removal of process. Using random oversampler. The oversampling is the process of adding more copies to the minority class. When dealing with constrained data resources, this approach is helpful. Overfitting and decreased generalized performance on the test set are potential drawbacks of the oversampling. This can be done with the help of random oversampler method, which is present in IMB Learn. This function randomly generates new data points belonging to the minority class with replacement by default. Synthetic minority oversampling technique, that is SMOOT. It is used to generate artificial or synthetic samples for the minority class. This technique works by randomly choosing a sample from minority class and determining k nearest neighbors. For this sample, then the artificial sample is added between the picked sample and its neighbors. Cost sensitive training. Cost sensitive training is machine learning technique in which algorithm is trained by taking into account the various costs connected to various kinds of errors. The cost of incorrectly classifying instances of one class may differ from the cost of incorrectly classifying instances of the another class in the typical binary classification problem. The goal of cost sensitive training is to incorporate these expenses into model training procedure. Threshold moving. In classifiers, predictions are often expressed as probabilities of class membership. The conventional threshold for assigning predictions to classes is typically set at 0.5. However, in the context of imbalanced class problem, the default threshold may not yield optimal results. To enhance classifier performance, it is essential to adjust the threshold to a value that efficiently discriminates between the two classes. Guinea impurity and entropy in decision tree. Difference between Guinea index and entropy. Guinea index is probability of misclassifying a randomly chosen element as a set, while entropy measures the amount of uncertainty or randomness in a set. In the Guinea index, the range of Guinea index is 0 to 1 and the range of entropy is 0 and log of C, where C is the number of classes. Guinea index is linear measure, entropy is logarithmic measure. Guinea is less robust than entropy and entropy is more robust. In Guinea, it has bias towards selecting splits that results in more balanced distribution of classes, and entropy has bias towards selecting splits that result in higher reduction of uncertainty. Guinea index is typically used in CART, that is classification and regression trees algorithms, and entropy is typically used in ID3 and C 4.5 algorithms. Guinea index is the additional approach to dividing decision tree. Purity and impurity injunction that are primary focus of entropy and information gain framework. Guinea index, also known as impurity, calculates the likelihood that somehow randomly picked instances would be erroneously catalogued. Guinea impurity is generally more computationally efficient than entropy. The graph of entropy increases up to 1 and then start decreasing, while Guinea impurity only goes up to 0.5 before decreasing, thus requiring less computational power. The range of entropy is 0 to 1, whereas range of Guinea impurity ranges from 0 to 0.5. Next question is, what is information gain? Information gain is measure used in decision trees to quantify the effectiveness of measure in the splitting dataset into classes. It calculates the reduction in entropy uncertainty of the target variable, class labels when the particular feature is known. Advantages of information gain. Simple to compute. Second is effective to feature selection. Third is interpretability. And limitations of information gain are it ignores the feature interaction. Information gain treats feature independently and may not consider interaction between features, potentially missing important relationship that could improve model performance. Second is bias towards features with many categories. Information gain features with the large number of categories or levels may have higher information gain simply due to their granularity, leading to bias in feature selection towards such features. Difference between information gain and mutual information. Information gain measures reduction in uncertainty of the target variable when feature is known, And mutual information measures the mutual dependence between two variables, indicating how much information one variable provides about other. Focus of information gain is individual feature importance and focus of mutual information and information exchange between the variable. Usage of information gain is commonly used in decision trees for feature selection, and in mutual information its versatile application in feature selection, clustering and dimensionality reduction. Information gain ignores the feature interaction, and mutual interaction considers mutual information considers the interaction between variables and computing in complex relationships. Computationally, information gain is simple to compute, and in mutual information computationally intensive for large dataset or high dimensional data. Why does overfitting occur in decision trees? Overfitting in decision tree model occurs when the tree becomes too complex and captures noise or random fluctuations in the training data, rather than learning and underlying patterns that generalize well to unseen data. Other reasons for overfitting include: first is complexity. Decision tree become overly complex, fitting training data perfectly but struggling to generalize to new data. Memorizing noise. It can focus too much on specific data points or noise in the training data, hindering the generalization. Overly specific rules might create rules that are too specific to the training data, leading to poor performance on new data. Feature importance bias. Certain feature may be given too much importance by decision trees even if they are irrelevant, contributing to overfitting. Sample bias. If the training dataset is not representative, decision tree may overfit to the training data and resulting in poor generalization. Lack of early stopping. Without proper stopping rules, decision trees may grow excessively, perfectly fitting the training data but failing to generalize well. Strategies to overcome overfitting in the decision tree models. There are two main types, that is in the pruning techniques. Pruning involves removing parts of the decision tree that do not contribute significantly to its predictive power. This helps signify the model prevents it from memorizing noise in the training data. Pruning can be achieved through techniques such as cost complexity pruning, which iteratively removes nodes with the least impact on performance. Limiting tree depth. Third is minimum samples per leaf node, feature selection and engineering, ensemble methods, cross validation, increasing training data. There are two main types of decision tree pruning, that is pre pruning and post pruning. Pre pruning or early stopping. Sometimes the growth of decision tree can be stopped before it gets too complex. This is called pre pruning. It is important to prevent the overfitting of the training data, which results in poor performance when exposed to new data. Sometimes some common pruning techniques are maximum depth. It limits the maximum level of depth in the decision tree. Maximum samples per leaf. Set minimum threshold for number of samples in each leaf node. Minimum samples per split. Specify the minimal number of samples needed to break up a node. Maximum features. Restrict the quantity of features considered for splitting. By pruning early, we come to be a simpler tree that is less likely to overfit the training facts. Post pruning, that is reducing nodes. After the tree is fully grown, post pruning involves removing branches or nodes to improve the model's ability to generalize. Some common pruning techniques include cost complexity pruning (CCP). This method assigns a price to each subtree primarily based on its accuracy and complexity, then selects the subtree with the lowest fee. Reduced error pruning removes branches that do not significantly affect the overall accuracy. Minimum impurity decrease prunes nodes if the decrease in impurity, Gini or entropy, is beneath a certain threshold. Minimum leaf size removes leaf nodes with the fewer samples than the specified threshold. Post pruning simplifies the tree while preserving its accuracy. Decision tree pruning helps to improve the performance and interpretability of decision trees by reducing their complexity and avoiding overfitting. Proper pruning can lead to simpler and more robust model that generalizes better on unseen data. What are the stopping criteria for decision tree? If we continue to grow the tree fully until each leaf node corresponds to the lowest impurity, then the data have been typically overfitted. If splitting is stopped too early, error on the training data is not sufficiently high and performance will suffer due to bias. Thus, preventing overfitting and underfitting are pivotal while modeling a decision tree, and it can be done in two ways. First is setting constraint on tree size and second is tree pruning. We have already seen the tree pruning. Let's focus on setting constraints on tree size, providing minimum number of samples for node split. Second is deploying the minimal number of samples for the terminal node, that is leaf, allowing maximum depth of the tree, vertical depth, and maximum number of the terminal nodes. Maximum features to consider for the split. How decision trees handle the missing values. Decision tree employ systematic approach to handle missing data during both training and prediction stages. Attribute splitting. The algorithm begins by selecting the most suitable feature based on measures like Gini impurity to separate the data. If a data point has missing value in the chosen feature, the tree will utilize the available data to decide which branch to send it down. When feature with missing values is chosen for splitting, decision trees consider the available data to decide appropriate branch. Decision tree is based on available non-missing values in the chosen feature. Decision trees seamlessly incorporate instances with the missing values into their decision-making process during both training and prediction. Weighted impurity calculation. When building the tree, algorithm chooses the feature that offers the best split at each node. When features with missing values is considered, algorithm calculates the impurity of both branches, one including instances with the missing values and the other without assesses the overall impurity of the data. The impurity of calculation is weighted based on the proportion of instances in each branch. This ensures that decision tree incorporates the impact of missing values when assessing the quality of a split. The algorithm doesn't disregard the missing values but rather weights on their impacts when evaluating impurity and making decisions. Surrogate splits. Decision trees anticipate and account for missing values during the prediction by using surrogate split. Surrogate splits are backup rules or branches that can be used when the primary split contains missing values. Decision tree calculates the surrogate splits during the training, considering the next best option for splitting when the primary feature has missing values. When making predictions, for instance, with missing values, the tree follows surrogate split to determine the appropriate branch. The anticipation of missing values in decision training allows the creation of surrogate splits, enhancing model's robustness during prediction. Some fly We have one example here. Imagine building a decision tree to predict a flight delays. Some flight might have missing data for weather attributes, so the approach will involve first is optimal feature selection. Decision tree starts by selecting most informative features for the initial split, such as time of the day. The goal is to create subset that best distinguish between delayed and non-delayed flights. Impurity calculation with missing data weights. As the tree grows, instances with missing weather data are encountered, so impurity measures like entropy or Gini are calculated. Taking into account the weights of instances where weather data is missing, this ensures that the decision tree considers the impact of missing values on the overall impurity calculation. Third is surrogate splits implementation. To handle missing weather data, subsequent nodes in the decision tree incorporate surrogate splits. Surrogate splits act as backup rules or alternative features like airline in case of primary feature, time of the day has missing values. This adaptive strategy ensures that the model can still make informed decisions even when certain features like weather are unavailable. By following these steps, decision tree adapts to missing data and maintain their ability to accurately predict outcome even when Certain features are unavailable. This adaptability strengthens the model's resilience in the real world application.